I'm sure you haven't forgotten this. Please, on the info sheet, it was brought to my attention yesterday, I made a reference goof. In the KSP data column, you see reference C on the info sheet, which you have a copy of. I believe the C follows silver sulfate as opposed to follow silver sulfide immediately above. Likely, if you've looked at this information, you recognize such, but make that fix. Now, another question or two regarding the confusion because of the overlapping 2046L final exams. This question is addressed to those of you who are not in position to take the 46 final on Saturday. Would you be in position to take the 46L and the 46 final both on Friday if I can get you started on the lab final at 5 p.m.? Anybody got a problem with that? Well, for those who are in attendance, that seems fine. The other possibility which comes to mind, I don't like it, that would be to run the 46L final on Thursday night, but you don't finish lab till Thursday. I don't like that one too well. But for that possibility, would anybody favor that over the 2 exams on Friday for those who can't take the exam on Saturday? If you would favor that. Well, chances are, whichever option you are preferring, I could accommodate you. Because if there's only a few, I could accommodate a few easily, as opposed, because then I won't need an auditorium space or anything like that. So based on the options I've just offered, for those of you who are not in position to take the exam Saturday, for the 2 alternatives, both exams on Friday, the 46L starting at 5 p.m. Pardon me. Yeah, for you folks. Or for 46L on Thursday night, and then 46 exam on Friday night. Tell me which of those options you prefer, with your name on it and a written note. Okay? We'll get this untangled. It's my fault I didn't see this in my very foggy, not good crystal ball when I drew up all this stuff at the start of the term. So you can blame me, but I'll do the best I can to fix it. Now, for those of you who didn't hear conversation regarding this section of chapter 19, where initially, regarding this material, you were looking at changes applied to the calcium hydroxide, calcium ion, hydroxide ion equilibrium. Changes to that equilibrium as a consequence of treating with various materials. You got through that. When you get to question 1918, which to my knowledge everybody got through, you were asked to consider the result of treating calcium hydroxide with ammonium ion. There's the reaction equation, here's the K value. Now you've done this investigation in 46L. Anybody remember what happened? Treat calcium hydroxide with ammonium ion. What happened? Did the calcium hydroxide dissolve readily? You bet it did. Unlike calcium carbonate. Calcium carbonate does not dissolve readily by ammonium ion attack. We've already done the analysis of that system. You remember the calcium carbonate ammonium ion? K is 7.2 times 10 to the minus 8. This K is 9.3 times 10 to the fourth. This K is considerably larger than 1, whereas that other K for calcium carbonate ammonium ion is a whole lot smaller than 1. So if nothing else, we're asked to recognize that the calcium carbonate is a much more stable material in the presence of ammonium ion. The facts are simply telling us that. Why might that be the case? Well, here ammonium ion is attacking hydroxide ion as opposed to ammonium ion attacking carbonate ion, and hydroxide ion is a lot stronger base. So here the acid-base attack on calcium hydroxide is much more effective. Secondly, and maybe you talked about this in 2045, I don't know. Did you talk about 2045 at all? In 2045, did you talk about the ionic lattice? I know you did the metal lattice, simple atomic lattice. Did anybody do ionic lattice? In the main, what does the strength of an ionic lattice depend on? In the main, what does the strength, the integrity, the structural integrity of an ionic lattice depend on? What does it depend on? The strength of the ion-ion bonds in the lattice, right? And what does ion-ion bond strength depend on mainly? Charge, D, E, N, S. Do I have to spell the whole thing? Charge densities? No, calcium carbonate, you got a +2 ion and a -2 ion. Here you got a +2 ion and -1 ions. Now the charge density of hydroxide ions are substantial. But when you arrange these things in a lattice, you see that in this lattice, per calcium ion you got to have 2 hydroxide ions. Whereas in the calcium carbonate lattice, per calcium ion you got 1 carbonate ion. That makes for a better lattice stacking pattern of the ions, the oppositely charged ions with respect to each other, gives you a more stable lattice. That comment is more or less in passing at this stage of the game, other than for the acid-base considerations, because that's part and parcel of what we're doing. So this is telling us calcium hydroxide is well expected to be dissolved readily by treatment with ammonium ion, because that's a huge K. So, simple stoichiometry question. At least I hope you find it simple. If I take a mole of calcium hydroxide and treat it with 1.0 liters of 1.0 molar ammonium chloride, how much calcium hydroxide will dissolve? What say you? How much? 0.50 moles. Right? Fraction equation tells you. If by this treatment you want to dissolve a mole of this, you need 2 moles of that. Well, here they're mixing a 1-to-1 mole ratio basis, so half the calcium hydroxide will dissolve. Now, questions 19, 21, 22, and 23 all relate to this transformation. Now to the calcium hydroxide attacked with ammonium ion, we're going to add sulfate ion. Will that support attack on calcium hydroxide? Well, if we don't do anything but calculate K, we see that for this transformation we got a lot bigger K than we got here. So clearly this, as strong an attack as this system is on calcium hydroxide, this is considerably stronger. Why so? Well, we still got the same acid-base attack, ammonium ion on hydroxide ion. But now we got sulfate ion going after calcium ion to make the semi-soluble material calcium sulfate. And how do the water solubilities of calcium hydroxide and calcium sulfate compare? We did this analysis. You studied this in lab. How do the solubilities, the water stabilities of those two materials, how do they compare? Which one's more stable in water? Which one's less soluble in water? Calcium sulfate. Which shows you why this transformation has a much larger, much greater thermodynamic drive. Question 1924 and questions which follow that are about conversion of calcium carbonate to calcium sulfate. By now, I should think that you can all write reaction equations as necessary. And if I ask you to go to the lab and make this conversion, and I put you to the side shelf, and I show you 1, 2, 3, 4 solutions, each of which contain sources of sulfate ion. Which of these solutions would you select to affect this transformation? You got sodium sulfate solution, ammonium sulfate solution, sodium hydrosulfate solution, sulfuric acid solution. I'll give you another hint. You investigated one of these transformations in lab. Remember which one you investigated? The one you investigated in lab was calcium carbonate treated with sulfuric acid solution. I'm just making a statement, hoping that you all remember it, but I don't know if you all remember it. Although I hope all of you who've done this remember it. Okay? So there's your reagent choice. 1 of 4. How many want to use this one? No looking around, you just look at me. If this is a crooked election, I run it. No, sometimes I wish to behave like Congress. How about this one? Can you argue that this attack is certainly better than this attack? Because here you got ammonium ion to help beat up carbonate ion. Here all you got is sulfate ion to go after calcium ion. Now how about this attack compared to this attack? How many like this attack better than this attack? Because here you got a source of sulfate ion, and you got hydrogen sulfate ion, which is a whole lot stronger acid than ammonium ion. Because the best ammonium ion can do is to convert carbonate ion to bicarb, at least from an effective conversion standpoint. But this stuff, that's a whole lot stronger acid than hydrated CO2. So if you hit this with this, what will you see? We see bubbles? You'll see bubbles all over the place. Will you ever see disappearance of white solid? Will you ever see disappearance of white solid? Calcium carbonate treated with 1 molar sodium hydrogen sulfate solution. Calcium carbonate treated with 1 molar sulfuric acid solution. Bubbles again. And better than sodium hydrogen sulfate, right? Because hydronium ion is a stronger acid by far than hydrogen sulfate ion. So bubbles again. Will you ever, for either of these systems, calcium carbonate treated with 1 molar sodium hydrogen sulfate solution versus sulfuric acid solution. For either of these treatments, will you see disappearance of white solid? Yes or no? No. But what will happen right before your eyes? Semi-soluble calcium carbonate will convert directly to semi-soluble calcium sulfate. And I hope you recognize that the sulfuric acid treatment is certainly the most effective attack of these. Because here, you have the same sulfate ion source as you have here, hydrogen sulfate ion. And here you got the best acid attack, hydronium ion. So in the main, all we're doing is applying knowledge of acid-base chemistry in conjunction with system PSI to get at this. You think this evening you might have to call upon PSI? Once or twice, maybe? 100 or 200 twices? 1,000 or 200,000 twices? Now then, the tail end of this section, or pardon me, the tail end of chapter 19, pardon me, page 1924. That follows the Lewis acid, Lewis base stuff that we did, the dissolving of silver chloride with ammonia, and then hitting that with hydronium ion and nitrate ion, reforming silver chloride and smoke above. And I pestered you, what's the smoke? And we finally got to that. Because, again, the most effective way to say something meaningfully about a chemical reaction system is to write the equation for the reaction or reactions that occur in the system. The equations which keep with chemical facts, not HCl, AQ, and that junk you see in textbooks. So if I take a sample of calcium carbonate and I treat it with ammonium sulfate solution, and all the calcium carbonate does not convert to the calcium sulfate dihydrate, which it won't, this equilibrium will be established. All right? Now you can calculate K for this equilibrium. You know how to do that. If you calculate K for this equilibrium, do you think you'll get a K value that's bigger or smaller than 1? It's not an easy question, but I'm asking for what you think based on the information with which at this stage of the game you should not only know but understand. How many vote for this thing you're going to get a K value bigger than 1? Smaller than 1? Didn't vote. 8 million points off tonight. I'm standing at the door with the exams. It's either 8 million points off or this time I won 10,000 bucks. And we'll really have a gala festival party at the end of the term. Okay. Smaller than 1. Because the stability of this far outweighs the stability of that. And by ammonium ion attack, you really don't remove carbonate from the system. Still in there, source of carbonate. Now then, how would I affect this conversion if I bubble in CO2 gas? Because when I bubble in CO2 gas to an aqueous system, at the minimum, what's got to happen? CO2 gas bubbled in the straight water. I get hydrated CO2, right? So I ask, in order to give this transformation a boost, calcium carbonate converted to calcium sulfate, will this boost the transformation? It will. Why? Because hydrated CO2 is an acid that is stronger than this? Yeah, that's right. Good. What if I hit this instead of this? I hit it with 1 molar acetic. Will this make the transformation even more favorable? If I hit this instead of this, but with this, will I now have a reaction for which the K value is a good deal larger than 1? Because acetic acid, strength-wise, compares how to hydrated CO2? It's stronger yet. So now, not only will I be attacking carbonate ion, now I'll be attacking carbonate ion far more effectively. And I will also be removing it from the system. Because now I'm going to get the bubbles and out the CO2 will go. All right? Now then, let's put the ammonium ion back. What impact do I exert on this equilibrium system if I've gone to the lab, in a beaker, I place some calcium carbonate in contact with ammonium sulfate solution? And now I add ammonia. Will ammonia affect this equilibrium? How is it that ammonia is guaranteed to affect the equilibrium? As things stand for this system, the only bases which are present in any kind of appreciable molarity in solution are what? It's on the board. Is this in the system in appreciable quantity? Yeah, I used ammonium sulfate solution. Is this in the system in appreciable quantity? No, because the K is small, but it's there. And this is present, but not in appreciable quantity. Well, now I'm going to say, let's make that in appreciable quantity. Let's put in some 1 molar ammonia. What effect is happening to this equilibrium? This way. Done. Back to chapter 20. We're now on page 20-7. We have so far recognized that the so-called composite thermodynamic equation which governs spontaneity is this, where delta G is our spontaneity term. If delta G for a reaction is minus, the reaction can go. If it's plus under the existing conditions, no. It can go the other way, but it can't go forward. Okay? Delta H for the transformation less T delta S for the transformation. So, we can say, as it follows from understanding that relationship, both chemically and algebraically, if delta H is XO, which means minus, favorable, bond improvement, and the change in entropy is also favorable. So for this system, the change in enthalpy as well as the change in entropy are driving the reaction. Well, that guarantees delta G to be minus. Guarantees reaction spontaneity. So if we turn the tables around, and delta H is endo, unfavorable, bond disimprovement, and delta S is also unfavorable, minus sign Y, then delta G is guaranteed to be plus. So in the forward direction, the reaction is non-spontaneous. It can't go in the forward direction. But it can turn around and go the opposite direction. So I've written here non or anti-spontaneous. Because if you have product components as well as reactant components, which you must have in order for delta G to have any meaning. Because if all you got is reaction components, if all you got are reaction components, and no products in the system, can delta G be plus? Can delta G be 0? Could a system be at equilibrium if you don't have any products? No. So for that case, the only thing that can happen is this thing goes. So that is, delta G is a condition-sensitive term. So if for the reaction system, with reactants and products both present, for the conditions under which the reaction is being studied, if we find delta G is plus, then what's going to happen is conversion of products back to reactants. Until what condition is established? Equilibrium. Now then, what if delta H and delta S are having a fight with each other? Delta H is endo, so the change in enthalpy is still against spontaneity, but delta S is plus. So delta S says, yeah, I like this reaction to go. System entropy is improving as a consequence of this chemical change. Delta G for this system, or delta GR, will be minus, provided the absolute magnitude of this compared to the absolute magnitude of this compare how? Which one's got to be larger? Which one? This one? Yeah. Because this is the favorable term. That's the against favorable term. Okay? So what do we do? Because we have only one control on this system based on the information on the board. What's the one control we have on the system and how it reacts, how it behaves? What's the one control we have? Temperature. So if I want to make T delta S to have a magnitude which exceeds delta H, because delta S is plus and delta H is plus, you want to heat the system up or cool it off? Heat it up. Well, let's turn the tables around. Change in enthalpy says, yeah, I like it, let's go. XO, bond improvement. But now the change in entropy is again it. Well, now we got to have this condition to get spontaneity. Okay? And finally, when delta H and delta S are in opposition to each other, as they are for this case and this case, then it's possible for the change in enthalpy to be equal to the temperature at which the system is being studied times the change in entropy. Change in enthalpy equals the temperature multiplied times change in entropy. Well, if these two are equal, then delta GR is 0. And now we're at equilibrium. And those are all the possibilities. So to apply and put to use this information, you've got to look at a reaction system. And apply what you know in conjunction with any information supplied to the system to make decisions on delta H being plus or minus, delta S being plus or minus. And if I were to ask you about something like water, I'm going to be a believer that you know that the normal melting point temperature of water is 0 centigrade and the normal boiling point temperature of water is 100 centigrade. I hope I can take stuff like that for granted. All right. So now we go to page 2010. We're jumping over to pages in between. We don't really need that stuff. It will follow as a consequence of what we are presently considering. Yesterday, I asked you about, when we started yesterday, talk about chapter 20, the meaning or significance of the superscript 0. That means the system is being studied under standard state conditions. And if I delta G 0 values reported, that means I've measured the change in free energy for the system under standard state conditions. Delta H 0, same thing. Measured change in enthalpy under standard state conditions. Delta S 0, same thing. Measured change in entropy under standard state conditions. So I wrote that here. What's sub F mean? Now, most of the time when I ask this question, students will respond formation. Well, if the question's worth 10 points, you just got 1. Because I want to know specifically formation of what and from what. Well, let's fix this of what. Let's put it amount of. I think that'll be more clear. Because I think you recognize, if I burn a small log in the fireplace, oak, and the next time I burn 10 large oak logs in the fireplace, when I burn the 10 large oak logs, I'm going to get a heck of a lot more heat liberated, right? So these terms are quantity dependent. So you've got to specify what kind of quantities we're talking about. And in chemistry, what is the way by which we most commonly refer to a quantity? Mole. So this means form 1 mole of the indicated product. No more, no less. Form 1 mole. 1 mole product. So we're going to be looking at a reaction equation in which the desired or designated product is to be considered to be present in the system 1 mole quantity. From what? What are we forming this stuff from? All right? To help you answer that, take a look at page 20-11. Page 20-11, you'll see reaction equations 1, 2, 3, 4, 5, small Roman, near the top of the page. See the reaction equations? One of those 5 reaction equations, and only one, by definition corresponds to delta H sub F super 0 for water liquid. One of those reaction equations, and only one, gives a delta H value which is equal to delta H sub F super 0 for water liquid. If you open up table 1 at the end of this chapter, chapter 20, a table which is rich in chemical information. you will see tabulated the delta H sub F super zero value for water liquid observed at 25 degrees centigrade. Now look at table 1. Keep your index finger or whatever have you at table 1, because we're going to go back to table 1 again in just a moment. And I'll go back to these reaction equations on page 11, 2011. And tell me which one of these reactions corresponds to delta H sub F super zero for water liquid. After I tell you that the formation from what is the required mole quantities of the component what? Elements. Because I can make water by all kinds of reactions. So for the sub F to have a fixed definition, so we all know what we're talking about when we use this symbology, we're considering forming water from the most stable required mole quantities of the most stable allotropes of its component elements. That's what it means. Now the component elements of water at a glance are hydrogen and oxygen. For hydrogen there are two allotropes. H atoms, H2 molecules. Which is the most stable allotrope? H2. Now then, for oxygen, how many allotropes? How many oxygen allotropes? Elemental oxygen. How many? How many?
4.
I'm not hearing many votes.
3.
Seems like we're getting at a consensus of 3. Do you agree with 3? Oxygen atoms, diatomic oxygen, and triatomic oxygen, commonly called ozone. Right? Those are all allotropes of oxygen. Which is the most stable? O2. So, what is the correct reaction equation? Number 3. All right, now just to try to be sure you've got this digested on your paper right now, I want you to write the reaction equation for which, if you measured the change in free energy under standard state conditions, you'd get delta G sub F super zero for this interesting material, Officers Candidate School. Right? Is that Officers Candidate School? Oh! Carbonyl sulfide. Well, we're not going to bother with carbonyl sulfide. Let's just call it OCS. And OCS under normal laboratory conditions is a gas, like CO2. If you operate on CO2 chemically so as to remove one of the oxygen atoms, replace it with a sulfur atom, you make this stuff. Write the reaction equation. While you do that, I'll clean this slate to continue with further progress. Now then, to answer this question, since clearly this material contains carbon in its composition, You have to decide or know which is the most stable allotrope of elemental carbon. Given that the only two common allotropes are what? What are the two common allotropes of elemental carbon? What? Diamond and graphite. Anybody got any diamond rings in here? Well, don't tell anybody. But how about, are any of you scrawling notes with a graphite pencil? Okay. Why aren't you scrawling notes with a diamond pencil? Don't you like notes which are scratches? Because diamond is awful strong and tough and durable. Whereas when you take a piece of graphite and shove it across your paper, you leave a smear of carbon on the paper. The graphite gives way, not the paper. But if you shove the diamond pencil across the paper gives way. And so will a desktop. And then the UF police will come over here and arrest you because you marred taxpayers' furniture. And you'll have to spend the next 84 years in a penal colony or something like that. Well, I don't know. All right. More on carbon graphite versus carbon diamond in a moment. So I'll write CGR, where the GR is a reference to graphite. Okay? OCS, ever so obviously, has a mole of carbon per mole of OCS. Okay? And this is solid. I think you know that. I think none of you in here writing with carbon graphite are using a liquid phase material or vapor phase. That would even be more unique. Look at my notes, Mom and Dad. They're all in gas phase. Ah! You opened my notebook. They went away. Oxygen. What's the most stable allotrope? Diatomic. So, for sub F, for this stuff, I need a half a mole of the most stable allotrope of oxygen. Now then, perchance you learned about this in 2045. I'm not sure, but I'll ask. Sulfur. What is the correct chemical formula for the most stable allotrope of elemental sulfur under normal lab conditions? S8. Phase? Solid. Amorphous, powdery, pale yellow, solid. And sulfur does not smell like rotten eggs. Hydrogen sulfide smells like rotten eggs. Sulfur containing stuff, but hardly sulfur. So, just for fun, in 2045, were you introduced to the structure of S8? It has a structure comparable to what organic chemists refer to as a crown ether, because the shape of the molecule looks like a crown. Zing, 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 crown. You see the nice points on the crown? How many corners for this sulfur crown? How many atoms in the crown?
8.
Well, then that's how many corners you got. What is that?
To write the equation correctly, we have to balance with the fraction coefficients? Or
Sure. You have no choice here. Because remember what the sub F means? Make 1 mole. You have no choice. There's nothing wrong with using fraction coefficients. It's just that they're a little bit clumsy arithmetically. Nothing wrong with it. But whole number coefficients are preferred. But when you deal with the sub F, now you're boxed into a corner. You have to use coefficients on the reactant such that you wind up with 1 mole product, no more, no less. Is that okay? All right. On we go. Go back to Table 1. In Table 1, I want you to look at the tabulated thermodynamic properties for carbon, graphite, and carbon diamond in Table 1. Okay? So you're looking at the tabulated thermodynamic properties for carbon, graphite, and carbon diamond in Table 1, from which you can answer this question. Which is the more stable allotrope of carbon? Well, you already know it's graphite, but now tell me why, based on the thermodynamic information at which you are presently staring. Well, let's look at this reaction. Because that form of carbon which has the lower enthalpy is the one with the stronger bonds and is the one which is enthalpically speaking more stable. Okay? For this transformation, what is the delta H0 value? It's in the table. Look at it. What do you see? Is that a plus or minus? Aha. So I'll just leave that. That's all we need to know to tell us this reaction is exo or endo. So it's bond weakening, isn't it? Now look at the S0 values. Because that allotrope of carbon which has the higher entropy, with the entropies being each tabulated at the same temperature, is from a thermodynamic standpoint the more stable form of carbon. Which has the higher entropy? Graphite. How about that? It's enthalpically more stable and entropically more stable than diamond. Do you not find this interesting, given that diamond you know to be a far tougher, more tenacious material? Well, let's take a look. Here's a model of carbon diamond. I know it's kind of clustered and cluttered. Not clustered, but cluttered. It's too compact. But maybe if I point, for example, at this carbon atom right here, you will see that carbon atoms bound to each other are in alternate colors to make model visualization a little bit easier. This black carbon atom, at which I pointed, has got 1, 2, 3, 4 nearest neighbor carbon atoms which are bound to it. So there's an extract of this part of this model from a Lewis structure standpoint. What is the carbon-carbon bond order for the carbon-carbon bonds in diamond? What's the bond order? 1. You got one bonding, one shared valence electron pair at each bond site. Bond order is 1. Okay? Now let's look at graphite. Notice that if I hold a model like this for graphite, number 1, you can see that any given carbon atom has got 1, 2, 3 nearest neighbor carbon atoms. So in the diamond lattice, each carbon atom is bound to 4 other carbon atoms, surrounded tetrahedrally, because that carbon in the center of that tetrahedron is how hybridized, like every carbon atom in the diamond lattice sp3. But here we have a carbon atom that's only bound to 3 other carbon atoms. And these bond lengths are shorter and stronger than those bond lengths. There I've drawn a Lewis structure representation of say, this section of my graphite lattice. What valence electron property does carbon graphite have, which carbon diamond doesn't have? What's it called? You see this picture? Could I just as well have written this picture like this? Same picture. So what's this property which I've illustrated for carbon graphite? Resonance, you betcha. This accounts for why carbon graphite is an electrical conductor. The pi electrons in carbon graphite are mobile throughout the carbon graphite crystal because of resonance. Not so for carbon diamond. Now, interestingly enough, carbon diamond is a marvelous thermal conductor. But electrically speaking, it's an insulator. Whereas graphite, electrically speaking, is a conductor. But these carbon atoms in the graphite lattice are how hybridized? sp2. So tell me, we recognize here the carbon-carbon bonds have a bond order of 1. What's the carbon-carbon bond order for the carbon atoms in graphite? What is it? 4/3. Isn't that a bigger number than 1? These bonds are stronger. That's why this stuff enthalpically is more stable. It's got stronger carbon-carbon covalent bonds. Well then, if this carbon graphite stuff has stronger carbon-carbon covalent bonds, how can it have a higher entropy than diamond? Now comes the other part of the puzzle. When you look again at the diamond lattice, you see every carbon atom is locked in a formal covalent bond network. Every one. Well, when you look at the graphite lattice, here you see a covalent bond network of carbon atoms with respect to each other in this plane. And another plane here and another plane here. Now I'm going to hold a model like this. See these really long sticks? Because what's happening when you write notes with your graphite pencil is you're taking this layer of carbon atoms and shearing it from this layer of carbon atoms. Because the attraction forces between this layer of carbon atoms and this layer of carbon atoms, represented modularly by these long metal sticks, are very weak. Much weaker than these covalent bonds. What are these attraction forces called?
Van der Waals.
Van der Waals or London, either one. And Van der Waals forces compared to covalent bonds, there's no comparison. The covalent bonds are enormously stronger. So bear in mind, when you write with your carbon graphite pencil, you are not breaking any carbon-carbon covalent bonds. No way. They're stronger than the carbon-carbon covalent bonds than in diamond. What you are doing is shearing carbon atom planes from other carbon atom planes and leaving behind on your paper a smear of graphite as a consequence of this shearing. And since the graphite lattice, from an overall stability standpoint, can be easily torn apart, provided you put the pressure on it in the right direction to shear these planes of atoms from each other. This has a lot more wiggle in its lattice than diamond. Now you can stare at diamond and stare at graphite, you won't see any wiggle. But if you could look at this with a really marvelous high-power electron microscope, you'll see the wiggle. Greater in the graphite than in the diamond, which accounts for the higher entropy of graphite versus that of diamond. Okay. And so, the rest of the stuff in chapter 20, pardon me, is really application of Hess's law, which you did in 2045. So I'm not going to say anything about that. And we'll go to chapter 21. What I want you to look at first in chapter 21 is what you see on page 21.1, phase diagram for water. Do you ever find it somewhat amusing or perhaps bemusing when people like those you find on the Weather Channel and they discuss water, all they mean is water liquid. If you see the solid water, that's ice. That's different from water liquid. Well, I agree. Phase-wise it's different, but chemically it's exactly the same. All water. So be careful with the word water, because that word itself does not tell anything about phase. Now, what does this phase diagram do? It shows you, as a consequence of applied pressure and temperature, what phase or phases of water are stable. This, I presume, you did in 2045. Now, when I mentioned this yesterday, I said, I don't know how you understand this in 2045 because this is a free energy diagram. Did it follow from what we've done over here so far? That if this equilibrium exists, and all you got to do, if you're operating at 1 atmosphere external pressure, like we have, practically speaking, in the laboratory at home, okay, is put some ice cube water in liquid water and insulate the system so that heat does not flow into or out of the system, which will maintain this equilibrium. Because if we don't let heat flow into or out of the system, the water solid, water liquid equilibrium will be preserved if you put ice cubes in water liquid. And again, insulate it so that heat can't go in or out. Because the only way you can make solid go to liquid is to put heat into the solid. And the only way you can make the liquid go back to the solid is to take heat away from the liquid if you're operating at constant pressure. Okay? So tell me, when this equilibrium exists, how does the free energy of water solid compare to the free energy of water liquid? The free energy. Because we've reminded ourselves over there, which by the time I got to it was obvious to you folks, that for this transformation, what's the value for this? 0. Okay. Just like for this transformation, delta G is 0. Now tell me, if for this transformation I want delta G, our super zero, to be 0, at what condition must this system be observed? If I want delta G sub R super 0 to be 0 for this. At what conditions must this transformation, must this equilibrium system be observed? If I want delta G sub R super 0 to be 0. What are the conditions? I'm listening. Because I ask questions like this all the time. Because I'm trying to find out if you understand what these thermodynamic terms mean. One atmosphere, what do you mean by this one atmosphere? What's that one atmosphere? Well, the pressure acting on the water liquid is one atmosphere. That puts it in its standard state. Doesn't matter how much water liquid you got. And the partial pressure of the water vapor has got to be one atmosphere, because that's when the gas is in the standard state. Okay? At what temperature does this condition exist? At an external pressure 1 atmosphere. 100 centigrade. Right? And the top condition has delta G sub R super 0 equal to 0 at what condition? What condition? What atmosphere external pressure and? 0 centigrade. Wonderful. Which means if this condition attends to this transformation, how much the standard free energy information for this stuff compared to the standard free energy information for this stuff? Standard free energy information for this stuff compared to the standard free energy information for this stuff. If delta G sub R super 0 is 0, how much do these compare? They got to be equal, can't they? I mean, they can't be anything but equal. Because delta G is the difference in these free energies. And in order for the difference in these free energies to be 0, they got to be equal. Okay? Now then, how do these values compare? For this stuff versus this stuff. Are these also equal? You wouldn't dare tell me that the bond strengths among and between water molecules in the liquid state are as strong as the bond strengths. That the bond strengths among and between water molecules in the gas phase are as strong as they are between water molecules in the liquid phase? Good, you wouldn't tell me that, because that'd be a lie. So which of these has the lower delta H sub F super 0 value? This one or this one? This one or this one? Gas or liquid? Remember, when I say lower, you got to pay attention to sign. Because when I see this, what does this mean? It means this. Right? Now, do you believe that these reactions are exothermic? Hydrogen with oxygen reaction is exothermic? Do you believe that? Do you believe that the dirigible Hindenburg in 1937 above Camden, New Jersey had one hell of a problem because of the exothermic nature of this reaction? You heard about the Hindenburg. It didn't last long after it got mangled up with the thunderstorm and power lines above Camden, New Jersey in 1937. Lighter than air. But you make an airship made with hydrogen contents, lighter than air, you betcha. But hydrogen reacts with oxygen awfully vigorously. So since these reactions are each exo, which one is more exo? Where you make the liquid or the gas? Which one is more exo? when you make the liquid, because you got bonds stronger between the water molecules and the liquid. Okay? So you got a bigger negative number for this than you have here, don't you? That's why this delta H sub F super zero value is lower, right? It's a bigger negative number. You got to let the science talk to you. You don't have a choice. But for these materials, how do their entropies compare? Hey, we haven't talked about this. This has a much higher entropy. So what you're seeing here is again a battle between delta H and delta S for this transformation. Because if entropy controlled this system, you'd only have water vapor. But if enthalpy alone controls this system, you only have water liquid. It's like up here. If only enthalpy controlled, you'd only have water solid. If only entropy controlled, you'd only have water liquid. Okay? So what you're seeing here is a condition when delta G sub R super zero, which is equal to these terms, this is equal to 0 because we're at 100 centigrade and the partial pressure of water vapor is 1 atmosphere. We'll pick it up from this point next time.